Okay, so welcome again, and today we will do something very interesting. So, just let me ask you, those who have studied about the fluid mechanics, I mean, the concept of the viscosity. Okay, so there are three important properties, uh, I mean, regarding the thermal science for any fluid. So, those properties are the mu, that is viscosity, K, that is thermal conductivity, okay, and lambda, that is coefficient of volumetric dilatation. Okay, so and these are related by Stokes hypothesis, right? Okay, this and this. So this I have proved, right? Stokes hypothesis. So either the Stokes hypothesis should be valid, or uh, the flow should be incompressible, right? Okay, so these three properties are very important, and if the Stokes hypothesis or the incompressible flow assumption is valid, then lambda is equal to minus 2 mu by 3. Now what should be the sign of this lambda and also the sign of this mu? So we can say that that mu should always be positive, but why mu, I mean, why mu cannot be negative? Okay, so that can be I mean, so this argument can be made on the basis of the physical considerations of viscosity. Okay, that is, the viscous force cannot augment the flow. I mean, if mu becomes negative, then there can be some situations where viscous force can be seen to augment the flow. But now, what about K? So about this property of thermal conductivity, this can be I mean, this can also be argumented by the Fourier's law of conduction, obviously. But now let us see that from the point of view of second law of thermodynamics. Okay, second law of thermodynamics. Okay, so second law of thermodynamics says that okay, so now let me give you a brief introduction about the property entropy. Okay, so I will not go into very deep. Okay, so Clausius inequality what does it say? That for any cyclic process, this thing should be less than equal to 0, right? This is equal to 0 for reversible processes, this is less than 0 for irreversible processes. And we also see that this del q by t cyclic is equal to 0 for any cycle, right? For any cycle, the cyclic integral of this quantity is equal to 0. That directly means that this must be a property. Okay, and we define this thing as entropy, or change in entropy. Rather, we define first the change in entropy. Okay, so this is change in entropy. So having defined this, now we have okay, so that means, so I mean, this is 0 only when this is for an reversible process. Okay, reversible process. And this is less than 0 for an irreversible process. Irreversible cyclic integral should be less than 0. Okay, so now having this concept further, now if we draw a graph of maybe so this is like any plane, TS, PV, or anything. So we have 2 points, 1, and 2, and then we will have two paths. Okay, and these two paths complete a cyclic process. Okay, so this is maybe path A and this is path B. Okay, now if we calculate the okay, so let me do some modification, that is this path is irreversible. Okay, and this path is reversible. Fine. So now what can we say? So ds cyclic integral, the cycle is 1 to 1. Okay, so now ds is a property, so this must be equal to 0, and now we can break this into two parts. So cyclic integral will not be there. It is 1 to 2 ds, right? Or okay, so let us proceed in another way, that is okay, so this thing is less than equal to 0. Okay, because this total actually this will be less than 0. Why? Because this cycle consists an irreversible process. So had the cycle, I mean, only consisted of the reversible processes, then we could have said that okay, this cyclic integral of del q by t, this should be identically equal to 0, but because this cycle consists an irreversible process, this must be less than 0. So the cycle is 1 to 1. Now let us break this into del q by t 1 to 2 plus del q by t 2 to 1. So this must be less than 0. So del q by t 1 to 2. So this path is reversible and this path is irreversible, right? So this is what? This is directly 1 to 2 ds, right? Plus, and this we say that we have this 2 to 1. Okay, so this is less than 0. Okay, now we can change this limit. So this is equal to minus 2 to 1. Okay, ds plus del q by t irreversible 2 to 1 this. Okay, so now if we combine these integrals, okay, irreversible 2 to 1. So for the path 2 to 1, this is true. Okay, so this, okay, and this should, I mean, now this integral, and this should directly mean, okay, so there is a minus sign here, right? There is a minus sign. Okay, so that means this thing irreversible 2 to 1, okay, plus something that is del si, okay, dsi. Okay, so this is, or dsg, let us write, because this is s generation. So this is dsg 2 to 1 is less than equal to ds 2 to 1. Okay, that is what have I done here. So if I take this ds, this integral ds 2 to 1 into this side, then this will be del q by t irreversible is less than ds 2 to 1, right? So this thing is greater than this thing, so I have to add some positive quantity here to make this thing and this thing equal. So I have just done the same thing. I have added this positive quantity. Okay, and this positive quantity is known as the entropy generation. Okay, entropy generation or production. Okay, so that means, so now if we omit the integral signs because everything is arbitrary, now ds is equal to, okay, plus ds generation. Okay, so this equation should be kept in mind. So second law of thermodynamics is, I mean, there are various statements of second law of thermodynamics, but the most important consequence of the second law of thermodynamics is this thing, that is, this S generation must be greater than equal to 0. This is equal to 0 for a reversible process, and this is greater than 0 for an irreversible process, right? Okay, so let us apply this principle into our energy equation, and let us say that what do I mean let us see that what do we get. Okay, so now recall the internal energy equation. Internal energy equation. So what was that? That was rho into so I think I used the symbol I for internal energy, capital I. So as far as I do remember, so this will be what? Del q double prime j del x j, right? And the stress component, the stress work, I mean the surface work, the component of surface work that should remain is tau ij del ui del xj. Okay, and what should be there? So so we got the internal energy by subtracting the mechanical energy from the total energy. So I mean this thing should also be there, right? Any other thing was there? Body force term got cancelled, and one of the components of surface work done got cancelled. So just, I mean, okay, so now let us proceed with this equation. Okay, so now we have the TS relation, that is TDS is equal to what? DI plus PdV, right? Now this equation has a very important significance, that is, this equation has been derived keeping in mind that the path is reversible, but after the derivation, this ds, this is the change of a property, so this is valid I mean irrespective of what path you are taking. That is why this equation is valid for any two points and for any two path, because this is essentially talking about the change in entropy, and that is a property which does not depend on the path, right? So during the derivation of this equation, we have applied that this del q is equal to TDS, okay, this thing, but this is only valid for an reversible process, but after the derivation this equation is valid for any process, just because entropy is a property. So just keep this subtle thing in mind. Okay, now so therefore if we apply now the material derivative, okay, so this will be di dt plus p into dv dt, right? And now let us multiply the rho, because we have rho into di dt in the internal energy equation, so this will be p rho this thing, right? Okay, so that means this rho, okay, now let me write it in this side, rho di dt into t rho ds dt minus p rho dv dt. Okay, okay, so now put this into this, and before that we have calculated this expression, right? So let us calculate this once more, and I always encourage you to do these things. Okay, I mean, whenever you forget anything, you try to derive that by your own. So two things you will get, two benefits. First is, if you have to I mean, remember the formula for any kind of examination, then that will automatically be embedded into your brain if you derive whenever you forget the same. And the second is, during the derivation, if you find any difficulty, that will show you that where the, I mean, at which part you are lacking the concept. So these two benefits you will get. So I always say that during GATE also, if you have the time, then whenever you are forgetting any formula, so to remember that there are two paths. One is, you should note down that formula in any one of your copy. You should preserve a copy for that and just see through that copy before going to bed. And the second one is, you should derive every time you forget that formula. Okay, so these two methods are very effective, and the second method is more effective. Okay, because, and the another benefit is that let us say that you are deriving a very big formula and there are various steps between the derivation. So in good examinations and interviews, they will ask questions from those steps also, and if you can derive that formula step by step logically, then those concepts and the logics behind those steps will be clear to you. So these are the benefits of deriving each and every formula step by step. So I don't remember the result of this thing, so let me derive it. So tau ij del uy del xj, and I will encourage you, if you have already seen the previous video on energy equation, so now you should stop the video. Okay, just press the pause button and try to derive this by your own. So this tau ij, now I remember this, and I remember this because only because I have derived this ample amount of times. Okay, so this will be k, I mean lambda into del u k del x k, okay, into delta ij plus mu into del ui del xj plus del uj del xi. Okay, so this was the tau, and this will be multiplied by del ui del xj. Okay, so this will be what? This del u k del x k. So this multiplied by this, I have said this earlier, this will be del u k del x k only, because this will be 1 when j equal to I, and so I can put here j. So del u j del x k, it is as good as del u k del x k, or you can put any other index, because it is a repeated index or a dummy index. So now mu into del ui del xj whole square plus this into del ui del xj, right? Okay, and after applying the Stokes hypothesis, we get that this lambda is equal to minus 2 mu by 3, so this will be minus p into this plus, okay, mu into phi. So this so this expression for this phi is equal to minus 2 by 3 minus 2 by 3, okay, del u k del x k whole square plus del u I del x j whole square plus del u j del x I del u I del x j. Okay, now your homework is just put here all the possible values of I and j, that is for I equal to 1 we have j equal to 1 to 3. For now this term will be summed over all, I mean those two indices, okay, because we have no free index here. I is repeated and j is repeated, okay. So likewise that you should expand this term into numbers, I mean instead of indexes you should put the numbers and you should expand this term and just do the simple algebra and show that this term is greater than equal to 0. Okay, this can be mathematically shown by the simple algebra. Okay, and if you face any difficulty just let me know in the comments. So I always I mean give you this type of opportunities so that you should get exercise. Okay, now and if you face any difficulty then you should always let me know in the comments and I will solve that. I will try to solve those things in the upcoming videos. Now okay, so we have derived the expression. Okay, so now we are ready. So now let us put this thing here. So sorry, now this will be t rho into okay, so let me just get this, okay, and I can copy this and I should paste this here, right? Okay, done. So the equation becomes t rho ds dt minus p rho dv dt is equal to minus del q j del xj plus this thing, okay, and what else, this term, right, minus p into, okay, so first let me write the positive term, this, and minus p into del u k del x k. Okay, so now let me drop this term, okay, heat generation term. So I am considering that heat generation is positive anywhere, but heat generation actually can be negative. Okay, heat generation can be negative. So for any reaction, maybe if it is exothermic then heat generation can be positive, and if it is endothermic then heat generation can be negative. Okay, so I want to see the effects of mu k and lambda only, so that is why I am omitting or avoiding or dropping this term heat generation or heat sink. Okay, so this equation becomes now, okay, let me do one thing. I can put this term into RHS. So P rho dV dt, okay, minus del Q J del Xj plus, okay, I am dropping this term, so this will be mu into phi minus this thing. Okay, so essentially this thing is what? I mean this term. So this term is nothing but we have shown that the volumetric strain, right? So I mean we have not shown, but in fluid mechanics actually this term is volumetric strain. And so what I will do is I will link a video about the detailed derivation of volumetric strain if any of you has to revisit that. Okay, so this term is volumetric strain, that is del V del T into 1 by V. Okay, so not del V del T, so this is 1 by V dV dt volumetric strain. So material, I mean, as we have taken a system, so material derivative. Okay. Okay, and this we can write as 1 by V is rho. Okay, so this term essentially becomes P into rho into this. So we can see this and this is cancelling out, right? That means this, so this thing becomes minus del xj, and now if we consider the Fourier fluid, so that then this will be this thing. Okay, so plus, so I am writing this down for Fourier fluid, Qj is equal to minus this thing. Okay, now from the Clausius inequality we have derived this relation, right, this thing. So that is ds equal to, so ds equal to del q by t plus ds gen. Okay, if it is a reversible, so if it is the reversible process, then this will be 0, and if it is an irreversible process, then this is non-zero, right? So okay, now so ds dt, okay, is equal to ds gen by t plus something change in q. I am still writing is that it as del q dot, because we have taken the time rate, sorry, I am sorry, it will be dt, so it will be del q dot by t. Okay, so how can we calculate this del q dot? Okay, so this del q dot can be calculated as this total del q dot. I mean this, I should write this as q dot. Okay, so q dot by t. Okay, so how can I now calculate this q dot by t? Okay, so this is basically the integral. Okay, so this will be the integral of what, del q dot by t all over the surface. Okay, because this is essentially the surface phenomenon. I mean, this is the heat transfer because of the heat transfer through the surface of the system or the CV. So here some heat is going and here some heat is coming out, and it is like that. Okay, so del q dot by t into dA. Okay, so now sorry, and one more thing, I have done a mistake here. I should write this as this thing, q dot nda, because heat flux is a vector. Okay, so if we now write this, so now from the Gauss divergence theorem we can turn into a control volume. So that will be divergence of q dot by t, okay, into dv. Okay, and these things we can write as, so let me, so these are the extrinsic property. Okay, so I should write it as capital S. So this thing, now this is for system. Okay, this is also for a system. Okay, so from Reynolds transport theorem I can write it as integral of rho small s dv del t. Okay, actually ddt, because this is a global property, and for the non-deformable. Okay, so let me write it in the next step. So this is cv plus cs rho s v, okay, dot eta or n dA. So in the next step I can write this as my del t. Now it should be del because now it is a local property, dv plus divergence of what, rho is v, v is a vector, dv. Okay, both are integrated over the cv, and this will be equal to this plus this, okay, into dv. And now at time t tends to 0, okay, del t tends to 0, so this cv should tend to, so as t is tending to 0, okay, at that limit cv, control volume, and control system, those actually merge. So these are the subtle concept of the Reynolds transport theorem, and I have talked about these things in earlier videos of my energy equation in the first video where I have introduced with the RTT. So this is, now this thing we can show that this boils down to rho into dsdt into dv. So this I have shown earlier, that how we can come from this to this. So this form is called as conservative form and this is non-conservative form. Okay, so this is control system. Okay, cs I have termed as my control surface, so this is system. Okay, similarly this term we can also, the second term also can be written as rho into ds gen dt dv. Okay, system. So this whole equation becomes what, if I take all the volume integrals together, so this plus ds gen dt dv is equal to what, this divergence of this thing dv. Okay, this is also system. So this was cv, but at the same limit, okay, t tends to 0, cv and cs, control system, those actually merges. Okay, so now so as dv is arbitrary and this function is assumed to be continuous, so these global forms can be converted into the local forms. So now ds gen, okay, so now, so rho into ds gen, okay, ds gen by dt is equal to nothing but this thing, okay, minus d rho into ds dt. Okay, now let us do some algebra. So that is, I mean calculus. So this will be divergence of this thing by t plus that will be what, okay, I should take this into this minus rho into ds dt. So this is the basic calculus, the multiplication rule of derivative, this plus, okay, so this will be minus 1 by t square, okay, q should be there and gradient of t. Now this thing, okay. Okay, so now let us use this thing. Okay, so this we have got as, so ds10 we have, so let me now revisit the equation. Okay, okay, it is correct, but one thing that q, I mean this thing is positive. So now I have told you this concept before. So if I consider this surface element, so outward normal is always positive, this n. Now if this q is entering, then it is taken as positive, and if this q is leaving, then it is negative. But if it is leaving, then only this n and this q will give a positive dot product, but if it is entering, then this q and n will produce a negative dot product. So that is why to make it positive, we should put a minus sign here, minus sign. So all where here also we will have a minus sign. Okay, so this minus sign should be there, so this will be minus, this will be also minus. Okay, so let me, okay, this all total will be minus, and this will be minus, and this will be plus, right? Okay, so now if we are done, I think I have done some silly mistake. What is that? Okay, so this was actually equal, okay, and this was plus. So I have done what? I have done this plus this equal to this. Okay, so if I have to put this into this side, then so here also I should have a minus. Okay, and if here I have a minus, then this will be what? This will be, so then this will be this minus this, right? So or minus this will be this minus this. Okay, so it is minus. Okay, so that means rho, I really apologize for this kind of mistakes. Okay, so minus gradient of q. Okay, so this will be, the signs will be inverted, this will be plus rho into dSdt. Okay, now done. So we have the expression for rho into dSdt here. Okay, so this is what this expression we have. So this is what? Del, okay, del square t, this thing, plus mu into phi, right? And there was a k, I think, the thermal conductivity. Okay, so okay, so this was what? Rho into dSdt, right? No, this was not rho into dSdt, so one t was also there, so I should divide it by a t. Okay, so now it is clear, right? Okay, and moreover, what was this actually? So I should have retained this form. So this was 1 by t into minus of gradient of q, right? So just let us revisit. Okay, so I am deriving these things after a long time, so that is why. Okay, so yes, this was what? Minus of gradient of q, and so and the same thing is here. Okay, because this I actually derived, minus gradient of q means what? Okay, del xj of qj, and qj means this thing, right? And k was there, So, and minus minus became plus, and by t was there because of this thing, right? Okay, so that means this del S gen by del t is equal to this. Okay, so let me write it below because I cannot fit it into a single line if I write it above. So del S gen by del t is equal to gradient of q by t minus this thing gradient of t plus, okay, plus mu phi by t minus gradient of q by t, right? So this and this cancels out. Now actually what remains? So what remains is this is equal to, so now for a Fourier fluid this is minus k into grad of t, minus k into grad of t. So this will be what? So this minus minus will be plus. Now k into grad t by t whole square, right? Plus mu into this by this. Okay, so now this is entropy generation and this is the rate of entropy generation. What? This is the rate of entropy generation. Okay, so from second law of thermodynamics, this should always be greater than equal to 0. Okay, now see, this quantity is greater than equal to 0. This quantity and along with the temperature is greater than equal to 0. Okay, so this was your exercise to prove that phi is greater than equal to 0, which is a simple algebraic exercise. So having these two things in mind, so this directly means that k comma mu should be greater than equal to 0 for rho into ds gen by dt, for this to be greater than equal to 0 for arbitrary temperature and velocity fields. I mean, you can argue that okay, if k is negative but this quantity is very large, then also it is positive. But if k is negative and this quantity is small, then it becomes negative, right? So for arbitrary, for any value of temperature and velocity fields, the second law of thermodynamics must be valid, and for that k and mu should be greater than equal to 0. Okay, and by Stokes hypothesis, lambda is equal to minus 2 mu by 3, then lambda must be negative. Okay, so these things are, I mean, very interesting actually, that by second law we can show that this k and mu are, I mean, should be positive and this lambda should be negative. Okay, now in fluid mechanics, the significance of lambda being negative is also interesting. Okay, so we have this term lambda with this divergence term, okay, lambda into del u k del x k, right? So it says that if we have already some volumetric compression positive, then the further, so as this lambda is negative, this total thing is negative if this is positive. So if this is positive, then there is some already volumetric expansion, right? Because this is the volumetric strain. So if this is positive, that means there is some already existing volumetric expansion, and this is the stress which augments this expansion. So if the fluid is already expanding, then the stress required to expand it further is negative. We don't require this stress actually. So this is the physical significance of lambda being negative. Okay, Likewise, that this k and mu can be also physically argued, that if you they can be argued like that I have said earlier, that that you cannot have any resistance that will augment the fluid motion. Okay, so then that will not be termed as resistance also, right? But I mean, everything, I mean, that is proved mathematically is more precise. So this is a very beautiful proof by energy equation, right? Okay, so I think we have almost covered every important aspects of energy equation. I will see through it, that if any of the topic is remaining, then I will cover it. And if if the energy equation is now finished, then we can move to something called the flow over a flat plate. So in fluid mechanics, the flow over a flat plate is studied extensively in the chapter boundary layer theory. But now we will study that if there is a temperature difference between the plate and the fluid, then how the heat transfer can be incorporated. Okay, how the heat transfer coefficients can be calculated, H. Okay, so up till then, goodbye and take care. Also, I say that if you have any doubt or question, just post in the comment. I will obviously try to answer that. And if you want me to cover any other topic, like regarding anything, okay, like I have appeared for GRE and GATE, and also various interviews like BRC, IISc. Okay, so I can help you for those things also. So until that, goodbye and take care.